This opening slide introduces Lecture 1 of the Module 1 Introduction to Digital Forensics series. It set the theme Foundation of Disciplines, which why society and investigators have become more aware of digital evidence and how the field has evolved from early computer crime work to modern digital forensic and incident response DFIR practice. Later lecture will deepen evidence handling processes, cyber threats, and tools. While this lecture builds the conceptual base, they will reuse throughout the course. These slides state what students should be able to do after the lecture. Define digital forensics scientifically, explain rising awareness of digital evidence, outline past, present, future development, apply introductory mathematics, hashing, and entropy, and run basic Kali Linux command for integrity checking and discovery. Emphasize that outcome mix theory and practice. For example, defining forensic is incomplete unless student can also show why a secure hash algorithm to 56-bit SHA 256 mismatch means an image may have been altered. This lecture outline is a roadmap of 6 blocks: foundation, awareness, historical evolution, mathematical foundation, Kali Linux labs, then summary and references. Encourage students to treat it as a checklist. After class, they should be able to give one concrete example under each heading, such as awareness illustrated by first responder photographing a phone screen before seizure, or math illustrated by hashing a universal serial bus USB image before and after acquisition. Digital forensic is the scientific process of identifying, collecting, examining, and analyzing data while preserving integrity and the chain of custody. Unlike casual looking at a personal computer, a forensic examination must be repeatable and defensible. Later labels computer forensics, cyber forensics, digital forensic, and incident response DFIR and network mobile cloud memory forensics are specialization of the same idea. For example, after a ransomware incident, a digital forensic and incident response DFIR team may combine disk imaging, random access memory, RAM capture, and firewall lock review under one case file with document hashes for every acquired item. Almost every modern dispute or crime leave digital traces: messages, cloud synchronization, closed circuit television, CCTV, network video recorders, NVRs, browser history, or Internet of Things sensors. Drivers include ubiquitous devices, cybercrime economics, and compliance needs. Goals include restructuring events, careful attributing actions, supporting legal proceedings, and improving security. The key principle is that digital evidence is volatile and fragile. Booting a seized laptop without right protection can change timestamp and overwrite slack space. For example, simply plugging a suspect universal serial bus USB device into an ordinary Windows personal computer PC may create auto-run artifacts and alter modified, assessed and created Mac times, weaken later courtroom testimony. The discipline is organized around identification, preservation, collection, examination, analysis, and presentation. Identification asks where might evidence live? Laptop, phone, email tenants. Preservation protect integrity. For example, write blockers, imaging. Collection acquire data under legal authority. Examination extract artifacts. Analysis interpret them in a context. Presentation reports finding to court or stakeholders. For example, in a harassment case, identification find the chat application backup, preservation images the phone, examination extract messages, analysis link them to a timeline, presentation produce an excerpt list with hashes. Digital forensic shares scientific ethos with fingerprints or deoxyribonucleic acid (DNA), work documentation, reproducibility, and peer review, but the medium is bits and metadata. Locard's exchange principle adapt well. Extract contact leaves traces such as registry keys, dynamic host configuration protocol laces, or residual file fragments. For example, when an employee copies a spreadsheet to a Universal Serial Bus (USB) device, traces may appear in Windows set up API logs, shellbacks, master file table, $MFT entries, and possibly the USB device own file system and logs to fibers transferred between clothing at a physical scene. Awareness has grown because courts, police, and boards now expect digital traces in most investigations. Smartphones, Internet of Things, IoT devices, cloud accounts, and wearable enlarge the evidence surface, while ransomware headlines and data protection laws force organizations to treat logs and devices carefully. For example, a traffic accident investigation today may include dashcam video, phone global positioning system GPS data, and vehicle electronic control unit ECU data, not only skid marks. So first responders need awareness training to avoid wiping or ignoring those sources. Different roles need different depths of awareness. Law enforcement and first responder must not power devices incorrectly. Incident response IR teams need acquisition skills. Lawyers and judges need authenticity concepts. System administrator must preserve logs. Human resource HR and compliance handle workplace cases. Cloud providers respond to legal process. Even, even end users benefit from basic hygiene. For example, a human resource manager who checks a laptop by logging in as the employee before calling information technology IT department may destroy evidence of who accessed files and create liability showing why non-specialists still need awareness rules. Awareness is driven by cybercrime markets, fraud, ransomware as a service, RAS, which is also known as RAS, media coverage of digital evidence in trial, academic programs, and certifications such as GIAC, Certified Forensic Analyst, also known as GCFA, and NCASE, Certified Examiner, NCE. Open source ecosystems, the Sleuth Kit, Autopsy, Vitality, volatility, and international standards such as International Organization for Standardization, International Electrotechnical Commission ISO, IEC 27037 and related guides. For example, a university that adds autopsy lab to its curriculum produces graduates who already understand hashing and case notes, raising the baseline competency of future investigators and corporate responders. Historically, the 1970s 80s saw ad hoc examination of disks in early computer crime cases. The 1990s formalized computer forensic with law enforcement toolkits. The early 2000s emphasized imaging standards, write blockers, and hash verification supported by landmark text and labs. Storage growth or Storage growth already outpaced analysis the needle in a haystack problem. For example, an investigator in 1998 might manually browse a few gigabit hard disk, and by the mid 2000s, the same case type could involve hundreds of gigabytes, forcing more structured imaging and keyword search. Current practice is multi-domain: disk, memory, network, mobile, cloud, and malware reverse engineering. Team balance live response against dead box imaging. Use automation for triage. and face cross border legal complexity with cloud providers. Evidence is often distributed, encrypted, and empirical. For example, investigating business email compromise (BEC) may require mailbox exports from Microsoft 365 endpoint, endpoint detection and response (EDR) telemetry, and phishing uniform resource locator URL analysis. No single disk image tell the whole story. Current digital forensic emphasize multiple domains, including disk, memory, network, mobile, cloud, and malware reverse engineering. Investigative teams must carefully weigh live response technique against traditional dead box imaging while utilizing automation for rapid triage and navigating cross-border jurisdictional challenges with cloud service providers because evidence is increasingly distributed, encrypted, and empirical. A single source is rarely sufficient. For instance, investigating a business email compromise incident typically demands the synthesis of Microsoft 365 mailbox exports, endpoint detection and response, EDR telemetry, and phishing URL analysis to reconstruct the complete attack narrative. Future directions include cloud-native acquisition application program interface (APIs), artificial intelligence, machine learning for triage, and timeline clustering, Internet of Things, vehicle industry control system forensics dealing with default encrypted and privacy constraints, and stronger tool validation standards. Research continues on formal correctness of tools and probabilistic interpretation of evidence. For example, a future vehicle investigation might pull encrypted telemetrics via manufacturer application program interface API under court order, then use machine learning to cluster anonymous strip pattern, raising new questions about tool trust and explainability. The table contrasts eras. Past focus on single personal computer PC disk and file allocation table FAT. New technology file system NTFS recovery. Present on multi-device digital forensic and incident response DFIR with memory, log and cloud. Future on scale and cryptography with application programming interface API, telemetry and end-to-end encryption. Use this as a memory aid. For example, recovering a deleted Word file from the home PC past scale remains useful. But today's ransomware case also need random access memory, RAM for keys, and cloud audit logs for lateral movement. While tomorrow's messaging case may hinge on provider side metadata when content is end-to-end encrypted, E2EE in future. Mathematics underpins trust and triage. Cryptographic hashes prove bit for bit integrity. Entropy estimates randomness useful for spotting encryption or packing. Timestamp require consistent time models. Without these ideas, the file look the same is subjective. For example, the two examiners independently hashing an evidence image to the same secure hash algorithm 256-bit SHA-256 digest can objectively agree the working copy matches the sealed original, which is a mathematical guarantee rather than a visual impression. A hash map arbitrary input to a fixed length digest and should be pre-image, second pre-image and collision resistant. Forensically, an image is considered integrity preserving when H acquired equal H original. Prefers secure hash algorithm 256-bit SHA-256 or secure hash algorithm 512-bit SHA-512. Message digest algorithm MD5 is historically common but cryptography weak. For example, after imaging a 64 gigabyte Universal Serial Bus USB device with DC3DD, the tool prints a SHA-256 digest. If later analysis changes even one byte of image file, the recomputing the hash will fail and alter the examiner that working copy was altered. For an ideal n-bit hash, finding a collision take roughly 2 to the power n by 2 trials. So message digest algorithm 5, MD5, 128-bit is around 2 to the power 64 and practically broken. While secure hash algorithm 256-bit SHA-256 is around 2 to the power 128 and currently strong. Students should understand why a MD match is weaker against an adversary who can craft collisions. For example, in a disputed document case, relying only on the MD5 to prove two files are uniquely identical is riskier than SHA-256 because sophisticated parties might exploit MD5 collision techniques. Shannon theory. Hx is equal to negative of sigma pi log 2 pi measures average information in bits. Uniform random bytes approach 8 bytes. English text is lower. Encrypted or complex blobs are near maximal. High entropy is a triage clue, not proof of malice. For example, scanning a disk image and finding a 2 gigabytes region with entropy is equal to 7.9 may suggest a 2-crypt or veracrypt container or packed malware payload, prompting deeper examination. Whereas a folder of plain text .text reports will show noticeably lower entropy. The practical segment uses free Kali Linux tools to verify integrity with hashes, estimate entropy, and discover basic artifact with the file string and find command. Tool name include SHA-256 sum, MD5 sum, ENT or Python files and string. Frame the lab as habit of mind. Every acquisition and every interesting file should leave a hash and a node. For example, learning goal after the lab, a student can take an unknown universal serial bus image, hash it, estimate whether a blob is encrypted, and extract printable string that look like universal resource locator or password. This slide shows how you create a sample evidence file. Compute secure hash algorithm to 56-bit SHA-256 and message digest algorithm 5MD5. Then alter one byte and rehash to observe the avalanche effect. Completely different digest. Discussion question: why image tool hash before and after acquisition? Example narrative evidence.txt containing case 001 evidence node yield digest A. Adding an exclamation mark yield digest B. This mirrors what happens if malware or an accidental write touches a forensic image during analysis. Let's do this small experiment. Now we need to echo any message, like in this case I'm writing case 001 evidence note 1, and I want this to be stored in some file, and in temporary folder I'm creating a file1.txt. Now I'll use SHA 256 sum tool available in Kali Linux to compute its hash value. So you can see it's showing the hash value for the particular file, and that file is having the content case 001 evidence node 1. Now if you I can compute MD5 sum for this as well using MD5 sum tool available in Kali Linux. So it has computed the MD5 hash value as well. Now let's make a change in the content. Now instead of writing case evidence 001, uh, case evidence 001 evidence note 1, I'll write case 001 evidence note 2, and I'll store in a different file. Now I'll use SHA 256 to compute its hash value. So you can see with the single character change, the total hash value is changed. Earlier, the hash value was starting with CEE4CA98, and now it is 354 AC and so on. So with a single change, the complete hash value get changed. So likewise, you can compute MD5 hash for this file as well, and you will find the complete change of hash value. So you can compare the MD5 hash values. Earlier it was starting with C4D7 and so on. Now it is 060CBD8 and so on. So the hash value with a single change get changed completely. We can do more experiment with MD5 sum and SHA256 sum tools. So one of the experiment is every empty file on earth has the same hash value regardless of the file name or the location. So for example, I'm creating two empty files, empty1 and empty2. So both are in temp folder, and then I'll use MD5 sum tool to compute the hash of both files. So you can see the empty files hash value for two different files, which are blank files, are same, are having a same hash value. So you can compute the SHA 256 hash value as well. So it will also give same hash value. So both of the empty files are having the same hash value irrespective of the hashing algorithm. Another experiment we can do with these tools is um, to show that a 1 byte file or a 1 gigabyte file produce hash of identical length. So let's suppose we generate hash of 1 byte. The message was X, so we generated hash of 1 byte. Now we'll create a 100 MB file with random data. So you can use this command to generate a file with random data, and presently we are creating a file which is of 100 MB. So the file has been created. Now we need to compute the hash of this file. So you can see whether it is 1 byte data or a size of a file of 100 MB is generating the same length, same hash length. Next experiment we can do with these tools is to compare how fast each algorithm processes the larger data. So we'll use the time MD5 sum slash big file which we have created. So this will tell you the how fast, how much time it has taken. So likewise, we can use the SHA 256 sum as well. So you can compare the time it has taken to hash the file. So we can go this with 512 as well. So it shows the timings. Here, the three timing should include the real time, which is a wall clock time, that is how long the command actually took from start to finish, just like a stopwatch. Includes time the process spent waiting, for example, the disk input, output, or other processes. The user time is the CPU time spent executing the program own code in user space. This is the time the CPU spent running MD5 sum SHA or SHA 256 or SHA 512 some instructions. The system time is the CPU time spent in kernel space on behalf of the processes. This includes the system calls, file input output, memory management, and other kernel operations. Next lab experiment is entropy estimation. So you can run ENT on binaries versus plain text. So ENT is a tool. Um, you can use the Python script to compute the entropy. So in this experimentation, we are comparing slash bin slash s with tiny text file shows how content type affects entropy edge. For example, encrypted random note attachment often sit near maximum entropy, while the ransom note text file itself, readable English, has lower entropy, helping in triage which carved files deserve entropy analysis first. So I'll come back to the experimentation bit later. So let us first understand what is entropy and what is its importance in computer science and computer forensics. The Shannon entropy measure how random or unpredictable the data inside a file is. So in digital forensics, we measure this on a scale from 0 to 8 bits per byte. A score of 0 means the file is completely predictable, like a document filled entirely with zeros. Normal text file and source code usually sit around 4 to 5.5. Compressed file like zips, JPEGs jump to around 7.2, while the fully encrypted files or packed malware binaries push all the way close to 8.0. Why is entropy important in forensics and malware analysis? Why should cybersecurity analysts care about entropy? First, it's a game changer for detecting hidden malware. Attackers love to compress or encrypt their malicious payloads to sneak past antivirus scanners. And a high entropy score immediately flags that something is hidden inside an executable. Second, it helps forensics investigation quickly tell the difference between plain text readable text logs and heavily encrypted containers like Veracrypt or ransomware files. Lastly, it allows us to test cryptographic keys and random number generator to make sure they are truly random and secure. ENT tool. So to calculate entropy easily on Linux, we use a classical command line tools called ENT, which stand for pseudo random number sequence test program. If you are using Kali Linux, it might already be installed, but if not, you can get it in a second using sudo apt install ENT. Using it is as simple as running ENT followed by the path to target file you want to inspect. Let's look at what the output actually look like. When you run the ENT on a file like this suspicious executable, it run a series of statistical tests and output the result. As you can see, our sample score an entropy of 7.92 bits per byte, which tell us it's important, completely random or encrypted. The output is simply shows that optimum compression would reduce its size by 0%, meaning we can't compress it any further. The rest of the metrics like the chi-square distribution, arithmetic mean, Monte Carlo pi estimation, and serial correlation all give us deeper mathematical proof of whether the bytes are distributed purely at random or if there are hidden pattern inside. Let's see the execution of entropy computation using ENT tool. You can compute entropy of a larger space like this. So this shows the statistics which I have just explained it to you. So likewise, you can compute the entropy of a small file like file 1 which we have created. So you can compare the entropy of the two, the larger entropy, lower entropy and the other statistics. So comparative analysis you could draw. So another way to do is using a Python script. So I have written a Python script in this file. So you can see this script. So it's accepting a script using the libraries to compute the entropy. So formula is applied to compute is computing the Shannon entropy. So likewise you can write the code for other entropy calculation as well. So you can execute this. So it will give you the Shannon entropy value. So either using tool or using coding, you can do this entropy computation. Likewise, you can do more experiments. For example, lab 3 is another simple experiment. Here you can use uh, the utility to identify type like string minus n 4 to extract printable text and find to list recently modified files under slash temp. These commands are foundational for later disk and memory work. For example, running string on a suspicious binary might reveal some URL like http double slash malicious.example slash gate and cmd.exe slash c, giving immediate investigation leads even before full reverse engineering. Now let us see the execution of these commands. So first one is the file command slash temp slash file 1.txt. So it will tell you the type of the file like ASCII text. So this command is to check the file type. Now next one is string file. So if you use string minus n 4 slash temp file 1, it will print the string inside this. So whatever is there in the file 1, that would be printed. Now next one is the find command. So you run the find command to see like file find slash temp minus type f minus m time minus 1 minus slash s 2 greater than slash dev null pipe head. So if you run this, it will show you the the recently modified files under the temp folder. So it will locate all those files. So again, the lab safety and ethics reminder. So practice only on authorized systems or laboratory images. Never write to original evidence. Document commands and hashes. Obtain legal authority before tooling. Ethics are not optional add-ons. For example, you practicing foremost carving must use a synthetic disk, sorry, not systematic, synthetic disk image from the instructor, not a classmate personal USB device containing private photos, because even a classroom demo can violate privacy and trust. So these are the references which you can refer. So these are some of the references. Another list of references is given in this slide. Thank you very much. See you in next lecture.